What's up, everybody? Today we're going to be talking about rockets. So welcome back. Let's get right into this new problem. So I've written it up on the board here. We have from the momentum balance of a rocket with a constant exhaust velocity, VE, derive VR, which is the velocity of the rocket, as a function of the mass of the rocket at that velocity and its starting mass, MI. Okay, so let's go ahead and start out by writing our momentum balance here. So we have some change in momentum, and if you remember, momentum from physics class is just simply m times v. With respect to time, we have some change in momentum with respect to time. Okay, and that simply is equal to the velocity, well, we'll say the mass in, the mass flow in, rather, times the velocity in minus the mass flow out times the velocity out. And then we also have to account for any other forces on our system, but in this case, it's 0. We're going to assume that the rocket is outside of Earth's atmosphere. Okay? And keep in mind when I write that mass flow out, I'm referring to the negative rate of change of mass with respect to time. Okay? So what I'm referring to here is the negative rate of change of mass with respect to time, because the mass is coming from the fuel inside the rocket, and it's being expelled from the rocket with respect to time. So we can say that that statement is true here. Okay. All right. So let's go ahead and keep working here. Next, we have the derivative of these two variables with respect to time. Well, both of these things change. It's not really a constant. We call it momentum, but it's both of these things combined. So what we can do is separate them, but we have to use the product rule, right? So that gives us m of the rocket, and I'll use a capital R here, dv rocket dt, okay, plus v rocket, I don't need to write the whole thing, dm dt equals, now looking at this side of the expression, we can take our velocities here, and what this really comes out to be is VR minus VE, okay? And times our mass flow out. And as previously stated, our mass flow out is simply the rate of change of mass with respect to time. So we can rewrite this as VR minus VE times dm dt. Okay, and you'll see now that some things start to cancel out. If we were to distribute this term to both of these terms, we would get rid of VR and VR times dm dt, okay? And we're left with mr times dvr dt is equal to negative VE times dmr dt, okay? Now, we can go ahead and separate our variables onto one side, right? So we get, let's leave dv, oh, well, our dt's cancel first, and we can leave dvr over here. Okay, and this is going to be equal to negative VE times dmr over mr. Okay, now let's go ahead and integrate both sides. We're trying to come up with a derive VR, right, as a function of mass. So let's integrate both sides now. So we have the integral of dvr, and we're just going to go from 0 to some VR, which I guess we should make a dummy variable for that, right? So the integration works. It's equal to the, can't forget the exhaust velocity first. It's equal to the integral of some initial mass to some final mass of dmr over mr. All clear. Okay. If we go ahead and integrate this, we're going to get VR equals negative VE times, we then have the natural log of m over m initial. Then we will get, if we take this negative and put it up top, right? Natural log rules, we get the exhaust velocity times the natural log of the initial mass over the mass. And this is our final expression for the rocket velocity. Okay, so I believe we've done it. That's all for this video, pretty short, and we'll see you for one last video.